Hello everyone, welcome to this new series of Modern Control Engineering. In this video, I would like to talk to you about Introduction to Modern Controls with Python. The three topics that will appear in this presentation are: first, modern control engineering, a key element in innovation such as robotics, automation, and manufacturing. Second, Python, a computation tool that helps model and simulate such systems. One tool that has become increasingly powerful for control engineering in recent years. And third, state space representation, which is a foundational concept in modern control engineering that enables efficient description and analysis of dynamic systems. 2 weeks ago at CES 2025 in Las Vegas, NVIDIA dropped a bombshell on the tech world with the announcement of their newest flagship graphics card, the RTX BlackWell 5090. Look at this video that's rendered with this new chip. This powerhouse takes real-time computer graphics rendering to a whole new level, delivering the performance that's smoother and more lifelike than ever before, from hyper-realistic game environments to jaw-dropping virtual production capabilities. The BlackWell 5090 is rewriting the rules of what's possible. The RTX BlackWell, the actual chip that generates these computer graphics, looks like this. The actual GPU at its core is about the size of a watch face. Yet, packed inside this tiny chip are an astonishing 92 billion transistors. This mind-blowing density is what makes the card's record-breaking speed and efficiency. We'll find another time to talk about the details, but modern control engineering is one key element of creating a processor that's capable of powering such incredible experiences. So that is why modern control engineering is important in applications such as semiconductor manufacturing and GPU manufacturing. Second, why Python? Python is a very powerful programming language. In fact, it has become the most popular programming language in 2025, according to the TIOBE index, or the Importance of Being Earnest index. Python was the top programming language in 2024. It's also the top programming language in 2025. Python libraries such as NumPy, SciPy, and Control make it an excellent choice for modern control engineering analysis. Third, why state space? In control engineering, a static system's output depends only on its present input. So a static system is also known as a memoryless system, where the output is impacted not by the past. The more broader class of systems, dynamic systems, are those where the present output depends not only on the potential current input, but also the past input. Let's consider snowboarding as an example of a dynamic system. This is a sport of dynamic balancing. There's no such thing as static snowboarding. A snowboarder's motion depends not only on the present force that acts on them, like gravity and friction, but also on their past movements, such as how they shifted their body weight or turned the board moments ago. This makes snowboarding a dynamic system because its current output or current motion is influenced by past inputs, such as the previous shifts in weight and angle of boards, etc. More specifically, the snowboarder must alternate between the toe edge and heel edge to create smooth S-turns. These transitions are dynamic because the current lean angle and force depends on the momentum and trajectory from previous movements. These turns are all continuous curved passes rather than 90-degree turns. You cannot make 90-degree turns because it's a dynamic process. When making a stopping maneuver is the same, the snowboarder has to gradually increase the edge angle and distribute their weight to create the drag and reduce speed. This is not an immediate stop either, as dynamic systems often cannot halt simultaneously, instantaneously, due to the inertia and momentum. Now we understand that the output of the dynamic system depends on past inputs, but how much past information is needed to describe this dynamic system? That is why state space becomes important. The concept of states is the information that you will need at the time that, together with the future values of the input, will let you compute future values of the output. Loosely speaking, state is the aggregated effect of past inputs. It is the necessary memory that the dynamic system keeps at each time instance. For example, consider a spring mass damper system. To predict the motion of this system, we need to know its current position and velocity, as well as the future force. In the special case, to dive a little bit deeper, in the special case when there's no friction and no spring, then the mass will travel at a constant velocity in a straight line. Furthermore, the motion is actually fully determined given the initial position, the velocity of the mass, as well as the time, the traveling time t. So therefore, the state variables for these dynamic systems are the position and velocity. These are the two variables that describe the motion, and together with the future force that act on the spring, act on the mass, will determine the future motion of the mass. We usually write the state variables in a vector. So we write state x is a vector that consists of the mass position and mass velocity. In this example, it's a 2x1 vector. And we write the state space description of the system as x dot, a first order differentiation of x, the state variable, equal to a times x plus b times u, and the output y equals c times x plus d times u. This is a first order ordinary differential equation, and it needs only first order. You don't need higher order derivatives in this state space description of the system. That's one of the main power for modern control engineering. It reduces a complex dynamic system to this first order general description model. When the state is chosen properly, taking the first order derivative will automatically reveal the full dynamics of the system. Here, in this case, if we take the first order derivative of x, we will get y dot, the derivative of the position, and v dot, the derivative of the velocity. Or equivalently, because the velocity v is the first order derivative of the position, then x dot actually is described as the first order derivative of y and the second order derivative of y. From physics, we know that the motion of the spring mass damper system can be fully described by this second order ordinary differential equation, where the acceleration or double derivative of y, which is the second element in the derivative of x over here, can be expressed as a function of y dot and y and u. So by expressing y double dot as a function of these variables, we can fully write the state equation in this compact matrix form, where the A matrix is a 2x2 matrix. The first row is 0, 1. The second row is negative k over m and negative b over m. the B matrix is 0, 1 over M, and C matrix is 1 and 0. Now, let us code the example with a few coefficients, M equal to 1, the K equal to 3, and B equal to 2. To put the system in Python, we use the control toolbox, so we import control as CO. We use the MATLAB plot library to plot a few time domain responses, and then we use the NumPy package to express the ABCD matrices. The state space system description can be formed by using SS in the control toolbox, and then we can print the system constructed this way and then do analysis about it. For example, we can obtain the step responses of the system using the step response function from the control toolbox, and then we can do a few plots of the time response. We can also use the initial response function to plot the initial value response. We can also use the impulse response function to plot the impulse responses. So let us put these into Python and do some live coding. There are different ways to run Python. It can be run from within the terminal, or it can run from as a script in software such as VS Code. In this demonstration, I will use VS Code, and I will use the terminal inside VS Code to run the demonstration. Let me make the window a little bit larger and zoom in a little bit more. So to run Python, you can just type Python within the terminal. You can check the version of the Python, for example, and then you can type in Python and then press enter to go into the Python environment. You can exit Python by pressing Control D, and then you can clear the terminal by typing clear. The demonstration, we will be using a few toolboxes. The NumPy toolbox, if you haven't installed these toolboxes, you can run pip install NumPy. I have already installed it on my computer, so it will say the requirement is already satisfied. So you can run pip install NumPy, pip install control, for example, and then also, so again, it will say the requirement is already satisfied. And you can also run pip install matplot library. These are the three toolboxes we'll be using today. Once you have done the pip install, you can go into Python and then start programming. We're gonna import the control toolbox as CO. We will import the MATLAB plot library, and particularly the pyplot function for plotting the time domain responses. We'll also import the NumPy library as np. Now let us define the state space system matrices A, B, C, D. So we'll run A to be a NumPy array, and then the first row of the matrix is 0, 1. The second row of the matrix is negative k over m. In our example is negative 3 over 1, and negative b over m, so it's negative 2 over 1. We can see whether we have done correctly by printing A on the screen. So in this case, you can see the format as well as the values are correct. The B matrix is a vector, column vector. We program it as a NumPy array 2. The first row is 0. The second row is 1 over m, and m is 1 in this example. We can again print B to see is the correct format and value. C is simply a row vector with the first row being 1, 0, and then D is 0. We can type it as numpy array 0. We can formulate the system description by typing sys to be equal to, in the control toolbox, we use the SS function, and A, B, C, D are the matrices. So we can print and see that the system is correctly formatted as a state space system with input U, output Y with 2 states. We can do some analysis. For example, we can obtain the transfer function of the system by using the control toolbox SS2TF function. This one will accept the system descriptions. I think it's gonna accept ABCD matrices, or as well as the system description itself that we have just formulated. We can print G and see this is the transfer function of the system. Okay, so we have formulated the system. Let us do some system analysis. We can run the step response, for example. So let's say T and Y out to be the step response of the system. And then we can plot this, we can print these on the screen first, for example, and see this is a long vector, and then same thing for the output. You can print them, and by using the plot function that we imported, let's open the figure first, and then plot the time domain responses. And then we can show the plots by typing PLT and then using the show function in this object. You can see the step response is popped up in this window over here. It does look like a step response with a final value around 0.35. We can also do similarly and obtain the, let's do impulse response of the system, and then plot again the input response and show it on the screen. So you can see again here in this pop-up window, the system impulse response is like this. It has a little bit of oscillation, and then it settles down very quickly within 6 seconds-ish. So that is the quick demonstration of how to program the state space system for the mass spring damper example. We can also use the power of object-oriented programming in Python and use another approach to plot these responses. We can use, for example, the same function in the control toolbox, step response. This time, instead of specifying the output of this function to be T and Y out in a format like this, we can specify a time response object, in this case called step response. And then you can print, this is actually a no longer a vector, but an object. You can see it's a time response data object. Inside, it has a few functions that we can call. We can say plot. Then this will plot the step response, and then we can use the plot show. The plot show this way, plot show Then you can see it's the same type of step response, but this time using the object-oriented program approach. So there you have it. We have finished talking about how to describe a dynamic system in the state space and the important concept of state. We have also performed some Python programming of an example state space system and analyzed its responses. Next time, we'll talk more about using Python to analyze and control dynamic systems. Stay tuned.